Am I clearly audible? Hopefully so.
Sir. Yes, sir.
Okay. So today we are going to discuss design of slab, and the load path. The load is first transferred to the floor, that is slab. From slab, it is transferred to beams. From beams, it is transferred to columns, and from columns, it is transferred to footing, and from footing, it is transferred to the strata. So now the slab is the first element which receives the load. And now let me share with you the entire screen so that I can show you how does the slab look. So Tanisha, is my screen visible?
No, sir.
Is it visible now?
Yes, sir.
Visible?
Yes, sir.
Yes, right, Tanisha?
Yes, sir.
Yeah, okay. So as you can have look at this picture, there are two things written here. One on the left hand side is one-way slab. The one on the other side is two-way slab. So I will explain what is one-way slab and two-way slab in a while. But look at this structure. You have a floor, that is slab, which rests on the beam. In the first case, there are only two beams on the opposite sides, parallel to the longer dimension of the slab. Whereas if you look at the right hand side, there are beams surrounding all edges of the slab. Are you able to see that, Tanisha?
Yes, sir.
Okay. And now let us try to understand what is one-way and two-way slab. So to demonstrate this, I will switch on my video. Just give me a second. Uh, okay. So are you able to see me? Tanisha, are you able to see me?
Yes, sir. Yes, sir.
So let me stop sharing so that the video will be clearly visible. Now have a look at this piece of paper. So what is its size? It is a rectangular in nature. Are you with me? Tanisha, are you with me?
Yes, sir. Yes, sir.
Yeah. Now imagine that this is supported on two opposite edges. And if you put any load in between, it bends in this fashion. Are you with me?
Yes, sir.
So this bending occurs only in this plane in which you can see the bending. There is no bending in the other plane like this. There is no bending like this. There is bending only like this. So we call such slab as one-way slab, which bends only in one direction. Are you with me?
Yes, sir.
Now imagine you have a slab which is squarish in nature, square shape in nature. Now, if it is supported on all the four sides, not on two opposite sides, it is supported on all the four sides. If I put anything in this, it is going to bend in this direction as well as it is going to bend like this. So you are going to get a saucer-like deformation. It bends in this direction as well as in this direction. Are you with me?
Yes, sir.
So such type of slab is called as two-way slab, which bends in two mutually orthogonal directions. So let me again share the screen with you. Uh, I hope you can see the one-way slab and two-way slab. Are you able to see that? Uh, so what are the points that differentiate one-way slab and two-way slab? Or when do we say that the slab is one-way or two-way? So it is mandatory that for two-way slab, you must have supports on all the sides. That means beams must be present on all the four sides. That is the first and prime most requirement. If you are going to have beams only on one opposite side, the slab is going to bend only in one direction and it is going to be one-way slab. So let me write down what are the conditions that are required to be satisfied in order to make the slab two-way. So let me share the whiteboard with you. Give me a second. I hope the whiteboard is visible to you. Is it?
Yes, sir.
So let me list down now the conditions which are required to make this slab one-way slab. Uh, to make this slab as two-way slab. So for the slab to be two-way slab, it must be supported on all edges by beams. That is the first and primemost condition to be satisfied for a slab to be two-way slab. What is the second condition? Second condition is the ratio of its span Ly by Lx, where Ly is the long direct dimension and Lx is the short dimension. This must be greater than or equal to 2. So let me demonstrate what I mean. So I hope you are able to see these slabs once again. Are you?
Yes, sir.
Okay. So what is Ly in both these cases? So the longer dimension of the two. So if you look at the first slab, you have this dimension. I hope you are able to see my arrow. So you have this dimension as shorter dimension and this dimension as larger dimension. So if the ratio of Ly by Lx is less than or equal to 2, then we call it that means this slab is more or less squarish in nature. Ly by Lx less than 2, then we call it as two-way slab. If Ly by Lx is greater than 2, we call it as one-way slab. Are you with me?
Yes, sir.
So let by mistake I wrote it as Ly by Lx greater than 2. Let me clear it. So what is the condition? The condition is the ratio of longer dimension Ly divided by Lx should be less than or equal to 2. Then the slab is two-way. If these two conditions are not satisfied, naturally it is one-way slab. So when the slab is one-way? When it is supported only on two opposite edges. Are you with me?
Yes, sir.
When it is supported on two opposite edges. So the supports are not there on all the four sides. The supports are there only on two opposite edges. And second condition, uh, Ly by Lx ratio is greater than 2 if it is supported on all edges. So there are two situations in which we call this slab as one-way slab. So if the slab is supported only on two opposite edges, by default it is one-way slab. We need not check Ly by Lx ratio. But if Ly by Lx ratio is greater than 2 and it is supported on all edges, but still as the Ly by Lx ratio is greater than 2, it is more like a rectangular slab and it will principally bend in one direction. So we call it as one-way slab. Are you with me?
Yes, sir.
Okay, now with this background, let us try to complete the design of one-way slab today. Hmm. There is a correction in spelling, so let me do that. F double O R. So design a one-way slab to carry floor finish of 1.5 kilonewton per meter square and imposed load of 5 kilonewton per meter square. So what is floor finish? The slab on which you are sitting right now, if you observe, there are going to be tiles on it. Those tiles are clinged to the slab with the help of mortar. So you are going to have that load which goes to the slab. Therefore, we call that load as floor finish. Are you with me?
Yes, sir.
So now let me draw the sketch of this slab. How does this slab must be looking like? So let me draw that sketch. Just give me a second. So this slab must look something like this. I am drawing a 3D view. I hope you are able to imagine this. Are you able to imagine this slab?
Yes, sir. Yes, sir.
So now uh, this slab must be supported on two opposite edges by beams. So those beams will that may be one of the beam may be this. Let me draw that. Uh, this edge is supported by a beam like this. And the other edge is also supported by a beam like this. Are you able to imagine this?
Yes, sir.
So if I look from this side, due to any loading that is acting on the slab is going to bend like this. So I will call this as view XX, view XX. So due to any load that acts on this slab, it bends in this fashion. So let me also give the nomenclature. Let me call this as X. Let me call this as X. Let me call this dimension as Y and vertical direction as Z. Are you with me?
Yes, sir.
Ah. So when I view from this side, I see the XY plane, isn't it? Sorry, XZ plane. This is X, this is Z. And how does this slab bend? It bends something like the diagram I have shown. Are you with me?
Yes, sir.
Okay. Now, as it bends only in this direction, therefore we call this as one-way slab. Now, let us do the load calculation. So, how do we design slab? We design slab as a beam of 1 meter length. So, this slab, this entire slab, we will divide into the pieces of 1 meter. So, let me draw those 1 minute. So, consider this strip. So, just a minute. Consider this strip. This width is 1 meter. Are you with me? So we can consider this slab to be made up of n number of such 1 meter wide strips. Are you able to imagine this?
Yes, sir.
Let me also start the video. I hope you are able to see this. Uh, are you able to see this?
Yes, sir.
So the slab is bending like this. Are you with me?
Yes, sir.
So we can consider this slab to be made up of n number of strips of 1000 meter width. So I will have 1000 meter width slip like this, then next 1000 meter wide strip, next 1000 meter wide strip, and each of this strip is independently bending in this fashion. ऐसे हम assume करेंगे. Are you with me?
Yes, sir.
So let me do that. So let us say this is the slab which bends like this. इसको and this is the 1000 meter wide strip. So let me cut this 1000 meter wide strip. So it looks something like this. Are you with me?
Yes, sir.
And it bends like this. So can I design this as a beam of 1000 meter wide and thickness equal to thickness of the slab? Are you with me?
Yes, sir.
And whatever is design that I get, I will keep it repeating in the other direction. So same steel, everything will be provided. Are you with me?
Yes, sir.
Okay, so let me stop the video. I hope you are able to see the whiteboard. Are you able to see the whiteboard?
Yes, sir.
Hello?
Yes, sir.
Okay. Now in this XX view, how do beams look like? So actually the cross section of this entire assembly will be seen something like this. Happy?
Yes, sir.
When I look from this side, so this basically is the slab. These are the supporting beams. Happy?
Yes, sir.
And now I need to know the span of this slab. This slab is going to bend along this span. So let me say L is the span of the slab, and let me say in the example it is given that the span is given in the example to be 4 meter. Are you with me?
Yes, sir.
So let me say that this span is 4 meter. Now perpendicular to this XY plane along Z direction, I will consider that this slab is having a width of 1000 mm. Are you with me?
Yes, sir.
And I will design a steel required in the 1000 mm. Same steel will be repeated in next 1000 mm. Happy?
Yes, sir.
Okay. So I'm going to design this slab very similar to the beam, but with width equal to 1000 mm and thickness is equal to slab's thickness. So let me show the slab thickness as this. So this is the overall depth of the slab. So overall depth is denoted by capital D. Happy?
Yes, sir.
Okay. So now let us go ahead with load calculations. Okay. I will take a new whiteboard. Is new whiteboard visible?
Yes, sir.
So let me go ahead with load calculations. So load calculations. So for that, what I'm going to do now is I'm going to draw the plan of the slab. How does the plan of the slab look like? So this slab has a span of 5 meter. That is given. So this is the span. How much is that? It is 5 meter. Happy? Are you with
Yes,
me?
sir. Yes, sir.
And I'm going to consider only 1 meter wide strip in this slab. So like this. So how much is this? Let me consider 1 minute. How much is this? This is 1 meter. Are you with me?
Yes, sir.
And this 1 meter strip, it will keep on repeating. So we consider this slab as these 1 meter wide strips placed one after the other, adjacent to one another. Happy?
Yes, sir.
Okay, so let me do the load calculations now. So I want to calculate the intensity of UDL on this beam. इस बीम के ऊपर क्या यूडीएल है वो मुझे देखना है. So this is the length. 5 meter is the span. So what I will do is I will do the load calculation on a chunk of 1 meter by 1 meter. Let me draw that. On the chunk of, no, 1 minute. Load calculation will be done on this chunk, which is having the dimension 1 meter by 1 meter. This is also 1 meter. So that I get UDL on this slab in the direction of the span, that is along the 5 meter. So what is the first load that we consider? The first load is dead load. Are you with me?
Yes, sir.
So dead load includes what? Dead load includes, no, before load calculation, we are going to do one more step. Let me do that step first. So let us move all this down. 1 minute. So what is the step number 1 that we do? Step number 1 is we decide the depth of the slab by something called as L by D ratio. So in this case, the L is 5 meter. So L is equal to 5000 mm. And in last class, I have told you that if the slab is simply supported, then L by D ratio allowed by the code IS 456 is 20 for simply supported. In last class, I have given you the list. If it is a cantilever beam, we allow L by D is equal to 25. If it is a cantilever, we allow L by D equal to 7. If it is simply supported beam, then we allow L by D equal to 20. And if it is a continuous beam, we allow L by D equal to 26. So for simply supported case, as this slab is simply supported over the beams, we consider L by D equal to 20. And out of that, what is the dimension L? So L is 5000. So I want this 5000 divided by D must be equal to 20. Are you with me?
Yes, sir.
Do you remember, Siddhi, last time we have given the deflection check for beams, where we said that L by D ratio should be 20 for simply supported, 26 for continuous, and 7 for cantilever. Do you remember that? Shreya, do you remember that?
Yes, sir.
Okay. So let us go ahead. So 5000 upon D should be equal to 20. That gives me, what should be the value of D? Tell me. Yes.
But it is 250.
200 and
50. 50.
250. Is it?
Yes, sir.
Uh, Let me look at the problem statement. 1 minute. What was the span? Oh, span is not 5 meters. Span is 4 meter. I think I made a mistake there. So it has to be not. Uh, this is not 5 meter. 1 minute. This is 4 meter. It is given in the problem. This is 4 meter. So in that case, this should not be 5000. It should be 4000 mm. And this should not be 5000 by D. It should be 4000 by D. Now tell me.
Sir, 200.
Okay. So therefore we require D equal to 200. And this is effective depth. Are you with me?
Yes, sir.
So what should I add in this? So if I draw the cross section of this slab, so if I draw this section, this one, section like this. So how does that section look like? So you have a slab like this, slab running like this. It continues. Now at the bottom, we are going to have reinforcement in this direction, which is running perpendicular to the plane of board. And we are also going to have a reinforcement like this. Let me show you the typical reinforcement of this slab. Are you able to see this diagram, Shreya?
Yes, sir.
So whether it is two-way slab or one-way slab, are you able to see that the reinforcement is running in both directions like a mesh?
Yes, sir.
So
Yes.
you have one layer going in the direction perpendicular to the plane of paper, other layer going in the direction parallel to the plane of paper. Are you with me?
Yes, sir.
So that's what I have drawn. So let me go back to the whiteboard. Are you able to see the whiteboard?
Yes, sir.
So when I take a section like this, I have one reinforcement going perpendicular to the plane of paper, which will be seen as these solid rounds. Are you with me?
Yes, sir.
And one reinforcement will be parallel to the paper, which will be seen like this. Let me draw it zoomed view here. So this is the slab. It continues. Now the reinforcement which is parallel, it will be seen like this. And it will be seen in double line because it's a bar. So this will be the bar diameter, isn't it?
Yes, sir.
So this is bar diameter 5. And you have the reinforcement going like this, perpendicular to the plane of paper. Are you with me?
Yes, sir.
So if I look at the center of this bar, from center of this bar till the top face of this bar, this is how much? It is 5 by 2, isn't it?
Yes, sir.
And how do we define effective depth? Effective depth is this distance, isn't it?
Yes, sir.
So you have got D equal to 200. So what will be the capital D? Capital D is overall depth. So how much is that? So let me write down that it is 200 mm, this small depth. Are you with me? Plus
Yes, sir.
5 by 2 plus 5, isn't it?
Yes, sir.
So once I do 5 by 2 plus 5, I reach the bottom surface of this reinforcement and then we have clear cover. Happy? So it
Yes,
is,
sir.
so it is 200 plus 1.5 times 5 plus clear cover. And how much is the clear cover that we provide? We provide 25 mm. Lecture चालू है. Bye bye. 25 mm. Are you with me?
Yes, sir.
So chalo. So we will now assume the phi. So let us assume phi as 12 mm. Let us say. So if I assume the phi to be 12 mm, can you tell me how much is capital D? 200 plus 1.5 times 12 plus 25.
Sir, it is 243.
And we cannot provide 243. We have to provide it in multiples of 10 mm. So we will provide it to be 250 mm. Are you with me?
Yes, sir.
So what is the outcome of this first step? The outcome of the first step is D should be equal to 250 mm. Are you with me?
Yes, sir.
Now let us calculate dead load. So dead load is to be calculated over this chunk 1 meter by 1 meter. Now can you tell me what will be the dead load due to self weight of this slab? Self weight of slab. So let me see how much it will be. So what is the volume of this 1 meter by 1 meter chunk? It is 1 into 1. Do you agree? Into thickness of the slab. How much is the thickness of slab? 250 mm.
Yes, sir.
So I'm going to consider it as 0.25. 0.25. Happy?
Yes, sir.
So this is the volume of this 1 meter by 1 meter chunk. Happy?
Yes, sir.
And what is the density of reinforced concrete? Density of reinforced concrete is 25. So this multiplied by 25 kilonewton per meter cube. So let me also write down the units. So what is the unit of 25? Unit of 25 is kilonewton per meter cube. Happy?
Yes, sir.
What is the unit of this 1 meter? It is meter. What is the unit of this 1 meter? Meter. And what is the unit of thickness? It is also in meter. Are you with me?
Yes, sir.
So what is the unit of this entire quantity? It should be kilonewton, but you have to understand that this is going to repeat every 1 meter. Are you with me?
Yes, sir.
So therefore its unit we write it as kilonewton per meter. Happy?
Yes.
So can you do the calculation and tell me how much it is?
Sir, it is 6.25.
6.25 kilonewton per meter. This is like a UDL on this portion of this slab. Why the unit is kilonewton per meter? वैसे देखा जाए तो ये multiplication का unit तो kilonewton आता है, but as we are calculating it only for the chunk of 1 meter and that keeps on repeating, therefore the unit is kilonewton per meter. Happy?
Yes, sir.
Okay. So we have considered self weight of the slab. Now we will consider floor finish. Above this slab, we have a floor finish. That means the tiles and all the assembly that makes these tiles stick to the slab surface. Uska bhi weight aayega. Are you with me?
Yes, sir.
So how much is that? So let me calculate that. That again needs to be calculated over this chunk, 1 meter by 1 meter. And uh, I hope this whiteboard is visible to you. Is it visible?
Yes, sir.
First one, yeah. So यहाँ पे क्या लिखा है देखो, design one way slab to carry the floor finish of 1.5 kilonewton per meter square. Happy?
Yes, sir.
So floor finish का unit किस में दिया है? It is in 1.5 kilonewton per meter square. Note that. Okay.
Yes, sir.
So how do we calculate this load? So what is the area of this 1 meter by 1 meter chunk? The area is 1 meter into 1 meter. And what is the floor finish load given? It is given in 1.5 kilonewton per meter square. Are you with me?
Yes, sir.
So what will be the unit of this product? So unit of this product is going to be kilonewton. Are you with me? However,
Yes.
as we are calculating this only for 1 meter along the span of the slab, therefore I have to consider it as kilonewton per meter. Are you with me?
Yes, sir.
So now tell me what is this? 1 into 1 into 1.5. So it is going to be 1.5 kilonewton per meter. Isn't it?
Yes, sir.
Okay. So we have now calculated the dead load of this slab. Now what is the imposed load or live load? So it is given in the problem that imposed load is 5 kilonewton per meter square. So again, acting on a chunk of 1 meter cross 1 meter. And what is the intensity? 5 kilonewton per meter square. Are you with me?
Yes, sir.
So it is going to be 5. This is going to be equal to 5 kilonewton per meter. Why per meter? तो unit wise तो kilonewton होना चाहिए, लेकिन we have calculated this only on a chunk of 1 meter by 1 meter. So यहाँ पे हमने सिर्फ 1 meter consider किया है along the slab span. Are you with me?
Yes, sir.
So it is 5 kilonewton per meter. So now these load calculations are over. Now let me draw the loading diagram. So how does this slab look like? So when I take a section like this, so let me draw the section direction this way. So along these long edges, we are going to have beams, isn't it? Are you with me?
Yes, sir.
So I'm
Yes, sir.
just drawing in the top view or in the plan of this slab, this dotted line. What this dotted line represent? There is a beam below. Are you with me?
Yes, sir.
So therefore, this is plan. In plan, at on two opposite edges, we have beam. And if I take the section like this, which is marked in red color, what do I see? So I see those two beams. Beams दिखेंगे. Are you with me?
Yes, sir.
And I'm going to have a look at. I'm going to see the slab. Are you with me?
Yes, sir.
What is the span of the slab? The span of the slab is given as 4000 mm. Happy?
Yes, sir.
And this slab spans between the beams. जैसे हमने beam को किया था, beam spans between the columns. The slab will span between the beams. Happy?
Yes, sir.
And what is the load acting on this slab? So there are two UDLs. One is UDL due to dead load. And how much is that? Tell me. 6.25, isn't it?
Yes, sir.
6.25 kilonewton. 1 minute. Kilonewton per meter. Happy? And there is another UDL. That UDL is due to live load, imposed load. How much is that? 5 kilonewton per meter. Happy?
Yes, sir.
So what is the total UDL summation of these two? However, we have not applied the partial safety factor for load here. So वो apply करना पड़ेगा कि नहीं पड़ेगा? So total UDL is going to be 1.5 times 6.25. 1.5 times 6.25 plus 5. So can you do this and tell me how much it is? 1.5 times.
Sir, it is 16.875.
So this is equal to 16.875 kilonewton per meter. Happy?
Yes, sir.
Now it is very easy. Now we have to design it like a beam having width of 1000 mm. Width कैसे दिखेगा हमें? इस प्लेन के परपेंडिकुलर प्लेन में वो हमने कितना कंसीडर किया है? ओनली 1000 mm. So it has to be designed as a width equal to 1000 mm, capital D equal to 250 mm, and small d equal to 200 mm. Are you with me?
Yes, sir.
So for beam design, what do we do first? We calculate the bending moment. So what is the maximum bending moment? So maximum bending moment is denoted by notation MUD, design moment, isn't it?
Yes, sir.
And how much is that? It is going to be WL square by 8 because it is simply supported slab. So it is 16.875. 16.875. Just give me a second. Sixteen point 875 into L square. L is 4. हाँ, अब जरा देखो मैं कौन से यूनिट में कैलकुलेट कर रहा हूँ. आई एम गोइंग टू कैलकुलेट इट इन किलो न्यूटन मीटर. सो स्पैन विल बी सब्स्टिट्यूटेड इन मीटर. 16.87 in kilonewton per meter. So 16.875 into 4 square by 8. So I will get the moment in kilonewton meter. Can you tell me how much is the moment in kilonewton meter?
It is coming as 33.75.
33.75 kilonewton per meter. Happy?
Yes, sir.
Are you with me?
Yes, sir.
Great. So this is the moment. And what is the shear force? So design shear force. Design shear force. For which shear force should I be designing this slab? I should be designing this slab for a shear force which is there prevalent at distance d from face of the support. ये हमने last time किया था कि नहीं?
Yes, sir.
The crack will propagate at 45 degree. So how much is this distance? This distance is from face of support. It is small d. Where is that small d? 200 mm. Are you with me?
Yes, sir.
So this is 200 mm d. So where should I calculate the design shear force at distance 200 mm? So how do I calculate that? I will have to draw the shear force diagram. How do I draw the shear force diagram? I will have to compute the reaction. So how much is this reaction and how much is this reaction? Half the total load. So that is 16.875 16.875 multiplied by 4 by 2. These many kilonewtons. So tell me, how much is this reaction?
Sir, it is 33.75.
AB 33.75. Okay, fine. Kilonewton. Are you with me? So this reaction
Yes,
is
sir.
also 33.75 kilonewton. Both the reactions are same owing to the symmetry of the problem. How do we draw the shear force diagram? You know how to draw it. So we have to rise by the reaction, then fall linearly, and on the other side you have to rise by the reaction. How much is this? 33.75, isn't it?
Yes, sir.
And how much is this? 33.75. So this is shear force diagram. Now where do I want to calculate the shear force? At distance 200 mm from here. So I have to calculate the shear force at distance 200 mm from here. And this occurs at the midspan. So how much is this distance? This is 2000 mm. Are you with me?
Yes, sir.
So go distance 2000 mm from midspan where shear force is 0, and you get the shear force of 33.75. Happy?
Yes, sir.
So go distance how much? ये distance कितना होगा फिर? 200, 2000 minus 200. So isn't it 1800?
Yes, sir.
So go distance. I will write it here. Go distance 1800 mm. You will get shear force of what? So tell me, how much is the shear force at this location? 1800 by 2000 into 33.75. So how much is it?
Sir, 1800 into 2000.
No, 1800 by 2000 into 33.75.
It is 30.375.
30 point.
375.
So this is the shear force for which you should be designing. Are you with me?
Yes,
So
sir.
we call it as VUD, and that VUD has to be equal to 30.375 kilonewton. Happy?
Yes, sir.
Okay. Now we know what is design bending moment. We know what is design shear force. Now the third is to compute. Third step is to compute area of steel on tension side. Are you with me?
Yes, sir.
And do you so to compute area of steel on tension side, first we have to prove that this section is under reinforced section. Then only we can use the formula which is used for under reinforced section. Are you with me?
Yes, sir.
So let me use Fe 500 grade steel and M20. If I'm going to use that, can you tell me what is the value of KUB? Or can you tell me what is the value of RUB? What is RUB?
Yes,
RUB
sir.
is,
Just a second.
yes, M for Fe 500 and M20. What is the value of RUB? मिल गया श्रेया?
Sir, just a second.
Yeah. Yes. Anyone else who can tell me the value of RUB? Shreya, did you get the value?
Yes, sir. Just a second. 2.66.
So this value is 3.66.
Sir,
Now, can
2.66.
2.66, is it?
Yes, sir.
Just give me a second. 2.66. Now, so what is the moment of resistance of a balanced section? So let me calculate that. Moment of resistance of balanced section is 2.66 multiplied by B into D square. So B is 1000 because we are considering the slab to be the beam of width 1000 mm. Are you with me?
Yes, sir.
So let me also draw the cross section so that we are on the same page. We consider this slab to be equivalent to a beam of width 1000 mm. Let me write down that 1000 mm and small d, which is equal to 200 mm. Small d equal to 200 mm. Are you with me?
Yes, sir.
And we are going to have the reinforcement in this fashion. Are you with me?
Yes, sir.
So reinforcement is going to be there in both directions. Both and D is 200 mm. So let me calculate MUB 2.66 into 1000 into D square. What is D? 200. So into 200 square. Happy?
Yes, sir.
So how much is this MUB? Tell me.
Sir, 106.4 into 10 raised to 6.
10. How much?
106.4.
No, no. Please type your message in chat box. 106. Is it?
Yes, sir. 106.4 into 10 raised to 6.
106.4. Let me write 1 minute. 0.4 into 10 power 6. But what is its unit? Its unit is in Newton mm. So to convert it into kilonewton meter, I will have to multiply by 10 power minus 6. So it is 106.4 kilonewton meter. Are you with me?
Yes, sir.
Now, is this greater than MUD? Yes. So it is greater than MUD. The moment it is greater than MUD, that means I am going to design the beam for moment less than this. It is automatically going to become under reinforced section. Are you with me?
Yes, sir.
So hence this section is under reinforced section UR, and we can use the formula for AST that we use for a under reinforced section, and that formula I have given to you in the last class. So let me find out how much is that. So just a second. That is 0.5 FCK upon Fy AST equal to 0.5 FCK. This divided by Fy 0.5 FCK upon Fy. Are you with me?
Yes.
This multiplied by this multiplied by in bracket multiplied by in bracket 1 minus square root of 1 minus 4.6 mu upon FCK PD square PD square. This bracket complete. This bracket complete into B into D. So what is the value of mu in our case? Here mu needs to be substituted in Newton mm. So mu is to be substituted as 106 into 10 power 6. Are you with me?
Yes, sir.
So can you substitute that and tell me what is the value of B? B is 1000. What is the value of D? D is 200. So sub FCK is 20. Fy is 415. Substitute all these values and tell me what is the value of AST.
Sir, can you repeat FCK and FY?
हाँ हमने FE 500 and M20 ग्रेड एज्यूम किया है ना. So FCK is 20 MPa and Fy is 500 MPa. So let me write down the value. FCK is 20 MPa. Fy is 500 MPa. 500 MPa. Then mu, the value of mu is 106.4 into 10 power 6. So 106.4 into 10 power 6. Value of FCK here is 20. Value of B is 1000. Value of D is 200. So can you tell me now how much is AST?
Sir, I'm getting it as 2.49
Hmm.
into 10 raised to 3.
3 point,
2.49.
2.49 into, let me cross verify 1 minute.
Yes, sir.
1 second. So AST is 0.5 into 20 upon 500 into bracket 1 minus square root of in bracket 1 minus 4.6 into 106.4 into 10 power 6. This divided by 20, this divided by 1000, this divided by D, that is 200 square. Outside the sign B into D, 1000 into D, that is 200. What? I got it as 1507.77. Has anyone got that? 1507.77. Can you cross verify, Shreya?
Yes, sir.
I think I am correct. Please cross verify.
Yes, sir.
Did you get this?
Sir, just a second.